Okay, let's unpack this. Welcome, everyone, to a deep dive into the online encyclopedia of integer sequences, the OEIS. For those of you exploring number theory combinatorics, you definitely know what an incredible resource this is.
Absolutely essential, I'd say.
Today, we're zeroing in on, well, a very specific sequence from this huge collection, OEIS A000242.
That's right. And our source material for this exploration today is simply the A000242 page itself, right from the OEIS website.
Make sense?
It's a really concentrated package of information about this one sequence, and our mission today is to really understand what that page is telling us.
And right away, what grabs you are the main descriptions. So
Yeah.
For A000242,
Yes.
it's introduced in two distinct ways. First, third power of rooted tree enumerator.
Okay.
And second, number of linear forests of 3 rooted trees.
They do sound quite different, don't they?
They really do. But the OEIS page, in its very concise style, it implies there's a deep connection here.
Precisely. And figuring out that connection is really the key to understanding the sequence.
So we'll break down both definitions.
Yes, we'll break them down, see how the page links them, and explore all the other bits of information it provides. It's like looking at the sequence from several mathematical angles at once.
Got it. And just a quick note for anyone tracking the history in OEIS or maybe other databases, the page does mention its old identifiers.
Yes, the M and N numbers.
M2798 and L126. But 000242 is the one we're focusing on today.
Right. A000242 it is. So where should we start? The terms themselves.
Yeah, let's do that. That's where many people look first. The OEIS page lists the beginning of A000242 as 139, 25, 69, 186, 503.
Yeah.
And, well, it keeps going.
Just looking at those numbers. 1, 3, 9, 25.
You might start looking for patterns, right? Differences, ratios.
Trying to spot something simple. But the page gives us some crucial context right away. The offset.
Yes, the offset says 3 years 2. What's important about that first number, the 3?
Well, that 3 going in the offset is vital. It tells us that the first term listed, the 1, isn't a 0 or A1, which you often see.
Right.
It actually corresponds to A3. So the sequence really starts counting things, you could say, from n equals 3.
Okay, so A3 is 1, A4 is 3, A5 is 9.
Exactly.
A3.
1, A4, 3, A5, 9, and so on. So any formula or definition on the page that uses n is assuming n starts from 3 for these terms listed.
That's a really critical piece of information. Okay, good. So let's dive into that first main description then. Third power of rooted tree enumerator.
Okay.
The page immediately follows this up by stating the generating function, or GF, for A000024 is bx cubed, BO3.
And this GF notation, this is the mathematical key, really, to understanding that first definition.
Okay.
The page clarifies that bx itself, this bx function, is the generating function for another sequence, A00000081.
A000081.
Yes, and A000081 is the sequence for the rooted tree enumerator.
Ah, okay. So A000081 counts rooted trees. What does that mean exactly? In terms of its generating function, bx.
So if you write out bx as a power series, like bx base b0 plus b1x plus b2 by 2 plus b3 by 3 plus and so on, then the coefficient, bn, is the number of distinct rooted trees that have exactly n nodes.
And a rooted tree is just a tree graph where one node is special, the root.
Precisely. One node is designated as the root. And A000081, that sequence starts 1, 1, 2, 4, 9, 21.
See, A1 means one rooted tree with one node.
Right.
A2, one rooted tree with 2 nodes. A3, two different rooted trees with 3 nodes.
Exactly. You've got it.
Okay, so Bx is like, well, you called it a catalog before. The coefficient of xn tells you how many rooted trees of size n exist.
That's a good way to think about it. Yes, a catalog.
Now, A000242's generating function is bx3. So you take that catalog, bx, and you cube it. What does cubing a generating function actually mean combinatorially?
Well, this is where the real beauty of generating functions for counting problems comes shining through.
Yeah.
The operation of multiplying generating functions. It has a direct combinatorial meaning. If you have, say, a generating function ax that counts objects of type A.
Where the xn coefficient is the number of type A objects of size n.
Exactly. And you have another one, bx, that counts objects of type B in the same way. Then the product, let's call it cx equals ax bx.
Okay.
That product cx is the generating function for counting ordered pairs of objects, one of type A, one of type B.
Ordered pairs?
Yes, ordered pairs where the total size of the pair is n. The coefficient of xn and cx ends up being the sum over all possible sizes I and j that add up to n.
I plus jn.
A 2 number of type A objects of size I times the number of type B objects of size j. It's a convolution.
Okay, a convolution. So if bx counts rooted trees by size, then bx squared, bx times bx, that would count ordered pairs of rooted trees.
Precisely.
Like a tree of size I and another size j combined somehow to make a total size of I plus j.
Exactly right. The coefficient of xn in bx2 would sum up all the ways to get a total size n by taking an ordered pair of rooted trees. Maybe one of size 1 and one of size n1, or one of size 2 and one of size n2, all the way up to size n1 and size 1.
And for each pair, you multiply the number of ways to get the first tree by the number of ways to get the second.
Yes. Each pair contributes the product of the number of trees of those respective sizes.
Okay, I think I'm following. So following that logic, bx3, that's bx, bx, must count ordered triples of rooted trees.
You've got it.
So the coefficient of xn and bx3 is the sum over all I, j, and k, such that I plus j plus kn of number of trees of size I times number of trees of size n times number of trees of size k.
That is exactly correct. And that combinatorial interpretation of bx3, well, that corresponds perfectly to the second definition given for A000242.
The number of linear forests of 3 rooted trees.
That's the one.
So wait, the term linear forest of 3 rooted trees is the combinatorial object whose counting sequence naturally has bx3 as its generating function.
Yes, exactly. A forest in graph theory just means a collection of trees. No cycles.
Okay, a collection of trees.
A linear forest of 3 rooted trees means a collection of exactly 3 rooted trees. The term linear, especially when you see it linked to a generating function like bxk, which naturally handles ordered structures.
Because of the convolution.
Right. It strongly implies that these 3 trees are being considered in a specific order. Think tree 1, then tree 2, then tree 3.
Ah, okay. That clarifies the linear part for me. It's not about the shape of the trees, but the fact that it's an ordered collection.
Correct. An ordered collection of 3 rooted trees.
So sequence A000242, starting at 3, 1, A430 vine, it counts the number of ordered triples of rooted trees. Tree 1, tree 2, tree 3, such that the total number of nodes across all 3 adds up to n.
Perfect.
Let's check that first term, n3. For n3, the only way to get a total of 3 nodes using 3 rooted trees is, well, each tree must have 1 node, right? 1, 1, 1.
That's the only way.
And we know from A000081 that there's only one kind of rooted tree with 1 node. A000000, count 1.
Correct.
So the number of ways is 1 for tree 1 times 1 for tree 2 times 1 for tree 3, which equals 1.
And then that matches A31.
It does. Okay, what about A403? Total size N4. How can we get 4 nodes from 3 trees?
Well, the possible size combinations, IJK, that sum to 4 using positive integers are 2, 1, 1, and its permutations.
2, 1, 1, 1, 2, 1, and 1, 1, 2.
Now, we need the number of rooted trees for size 1 and size 2 from A00000081, A10, A1.
Okay, so for the triple 2, 1, 1, the number of ways is A2, A1, A1 equals 1, 1, 1, 1 is 1.
Right.
For 1, 2, 1, it's A1, A2, 1, 1, 1, A1. And for 1, 1, 2, it's A1, 1, A2, 1, 1, 1, 1, 1.
So the total number of ways for N4 is
1 plus 1 plus 1 plus 1, 1, 3, which matches A43.
Exactly. See, the terms line up perfectly with that combinatorial interpretation that comes directly from bx3. The generating function is the elegant bridge between the abstract idea of cubing the rooted tree enumerator function and the concrete act of counting these ordered sets of 3 rooted trees.
That really is a beautiful connection.
Yeah.
It shows how generating functions aren't just, abstract mathematical tools. They're also a language.
A language for describing combinatorial structures and operations on them, yes. It's really fundamental in combinatorial enumeration.
The structure of the thing you're counting often dictates the form of its generating function.
And how it relates to the generating functions of maybe simpler component parts. In this case, the components are individual rooted trees.
Okay. Beyond the generating function and these 2 core definitions, the OEIS page offers other kinds of information too. There's an asymptotic formula listed.
Ah, yes, the asymptotics.
It says AN is asymptotically equivalent to, 3 times A18770 times A0051491 to the power of n divided by n to the power of 32.
Right. An asymptotic formula like that is incredibly useful, especially when you're interested in very large values of n.
It tells you how fast the sequence grows.
Essentially, yes, the growth rate. It's not an exact formula for an for any given n, but it provides an excellent approximation for terms way out in the sequence.
And it shows it grows roughly exponentially because of that A05149 term.
Correct, but with a polynomial correction factor involving n to the minus 32 power.
And what's fascinating here is that the formula itself uses other OEIS sequences, A18770, and A051491.
Yes, that's very common in OEIS. It really reinforces this idea of the OEIS as a highly interconnected network of sequences, not just a flat list.
Right. The page for one sequence often acts as a kind of hub, linking out to related concepts and other sequences that are important for understanding it.
Precisely. You see these connections explicitly laid out in sections like cross-refs and CF on the A00242 page.
Like it notes, A000242 is column 3 of sequence A339067.
Which suggests it's part of some larger table or array of sequences, likely related by some parameter.
And the CS section, the compare section, lists related sequences. It includes, crucially, A00000081, the rooted tree enumerator we discussed.
The core connection.
But also A000106, A000300, A00000395. Exploring those links could presumably reveal deeper structural relationships.
Absolutely. Between different, perhaps seemingly different, combinatorial counting problems.
The page also helps place A000242 contextually. It has index entries for sequences related to rooted trees.
Yes, that confirms our understanding. It's officially part of this well-defined family of sequences that are important in studying trees and graphs within combinatorics.
Very useful categorization for researchers navigating the database.
Extremely helpful. It helps group sequences that share structural properties or maybe arise from similar combinatorial questions.
What other sorts of information does the page offer?
Well, it includes keywords like non, easy, and nice.
Non just means non-negative terms, right?
Yeah.
139, they're all positive.
Correct. Easy and nice are a bit more subjective, not formal definitions, but they offer hints.
What might easy suggest in OEI's context?
It might suggest a relatively straightforward definition, or maybe a simple recurrence relation or formula exists, even if the terms grow quickly.
And nice.
Nice often implies the sequence arises naturally in significant mathematical contexts, or maybe has particularly elegant properties, like its generating function connection here.
Makes sense. It also notes the author of this specific OEIS entry.
N.J.A. Sloan.
The founder of the OEIS himself.
Which is a direct link to the history of the database, yes.
And it provides historical references too, pointing to published mathematical literature, J. Riordan from 1958.
A classic text in combinatorics.
And Sloan's own books, a handbook of integer sequences from 1973 and the encyclopedia from 1995.
These references are important. They show this isn't just some obscure sequence someone recently made up. It was studied and documented in major combinatorics texts decades ago.
Gives it historical weight.
And context within the field, exactly.
The page also seems to highlight the community aspect of OEIS. It mentions contributors who have extended the sequence.
Yes, like T.D. No providing more terms, and Christian G. Bauer providing further extensions or related sequences.
So it's a living database.
Very much so. It's a collaborative project. Contributions from mathematicians, programmers, enthusiasts all over the world constantly expand and enrich it.
And for people who want to actually use the sequence, computationally.
There's often code provided.
Yeah, it shows code snippets here. Maple Mathematica, attributed to Eloa P. Hines and Jean-Francois Alcover.
Which is invaluable for practitioners, right? It lets anyone generate terms of the sequence programmatically.
Verify calculations, use it in their own research.
It directly connects the abstract definitions to concrete computation.
And finally, there are administrative details. Status is approved. Last modification date, June 6, 11.4 EDT, 2025. Shows it's actively curated.
Right. So altogether, all these pieces of information on just this one single OEIS page, they provide a remarkably complete picture of the sequence.
You get the numbers?
The numerical values, yes. Multiple conceptual definitions, the underlying mathematical structure through its generating function.
It's asymptotic behavior, how it grows.
Historical context, connections to other sequences, computational tools. It's incredibly information dense.
So wrapping up our deep dive into E000242, we've really seen how the OEIS page acts as this powerful summary. It gives the terms, clarifies the starting point with the offset.
Crucial.
And offers those two key definitions, third power of rooted tree enumerator and number of linear forests of 3 rooted trees.
And I think most compellingly, it shows how those two views are fundamentally linked, explained by the generating function b by 3.
Right, using the power of generating function multiplication to count those ordered triples of rooted trees.
Exactly.
We also saw how the page gives all that vital supplementary info, asymptotics, links to related sequences, its place in the study of trees.
Historical references, code.
Yeah. It's really a prime example of how an OEIS entry efficiently packages such diverse mathematical information about just one sequence.
It really is. For number theory students, for researchers, really anyone working with sequences, learning how to effectively read and interpret these OEIS pages is just incredibly beneficial.
And for you, the listener, maybe think about how often these seemingly different counting problems in math
Like just counting trees versus counting specific arrangements of multiple trees.
can be unified and understood through this, well, elegant machinery of generating functions. A000242 is just one example, but it points to that deeper interconnectedness.
It really illustrates a powerful theme, doesn't it? The same sequence can pop up from multiple, seemingly unrelated combinatorial descriptions.
And generating functions are often the tool that reveals their equivalence.
The key that unlocks the connection.
Which leaves us with a final thought to maybe ponder. How many other sequences might you encounter maybe in your own studies or explorations that, like A000242, have multiple faces, multiple definitions that are only revealed to be the same thing when you look at them through the lens of generating functions? A really powerful invitation, I think, to always be looking for those hidden connections.